Given an array sweetness where each entry is one consecutive chunk sweetness, and an integer k, make k cuts to split the bar into k plus 1 consecutive pieces. You eat the piece with the minimum total sweetness and give the other pieces to your friends. Find the largest possible value for that minimum piece when the cuts are chosen optimally. Example 1, sweetness runs from 1 through 9, and k equals 5, so we need 6 pieces. One optimal cut pattern groups 1 2 3, 4 5, then 6 alone, 7 alone, 8 alone, and 9 alone. The piece totals are 6, 9, 6, 7, 8, and 9. You take the smallest piece, which has total sweetness 6, so the answer is 6. Example 2, 9 chunks and k equals 8, so we need 9 pieces. There is only one way to cut between every chunk. The smallest single chunk has sweetness 1, and that is the piece you must eat. Output 1. We want to divide this chocolate bar into exactly 6 pieces so that when our friends take the 5 largest pieces, the remaining piece we get is as large as possible. If we greedily make some pieces massive, we accidentally leave behind a tiny crumb. Because we get the absolute minimum piece, a single bad cut ruins our entire share. We need a strategy that keeps the pieces balanced. Finding the optimal cuts all at once is incredibly hard because every single cut dynamically changes the value of all the others. So, let's flip the problem completely upside down. Instead of guessing cuts, what if we guess a target sweetness value, x, and see if it's physically possible to cut the bar so that every single piece meets or exceeds that value? Before we start guessing target values, we need to establish a strict floor and ceiling for our search. What's the absolute worst-case minimum piece we could get? It's simply the smallest single element in the array, which is 1. What's the absolute best-case maximum? If we didn't have to share at all, we'd get the total sum of the entire bar, which is 45. Our optimal answer is guaranteed to live somewhere within this clear window from 1 to 45. Testing a target value is simple and greedy. We walk down the chocolate bar from left to right, adding up sweetness. The moment our current chunk hits or exceeds our target of 5, we instantly make a cut. If we can successfully manage to get 6 or more pieces this way, it means our target of 5 is totally doable, and maybe we can aim even higher. But if we aim too high, say, demanding a minimum sweetness of 15, we have to combine too many segments just to satisfy the first few people. We run out of chocolate completely and can only form 2 pieces instead of the 6 we need. This tells us a target of 15 is completely impossible. Notice the beautiful pattern emerging. Low targets are always possible. High targets are completely impossible. There is a clean, sharp boundary line where the choices flip from possible to impossible. Our ultimate goal is to find the absolute highest possible target right on this boundary. Since this search space is perfectly sorted, we don't have to check every number one by one. Instead of guessing blindly, we use binary search to cut our search space in half with every single guess. We pick the midpoint. If it's impossible, we throw away the upper half. If it's possible, we store it as a potential answer and shift our floor upward to see if we can do better. By squeezing the boundaries together, we will pinpoint our optimal maximum sweetness in mere microseconds. We kick off our solution by defining our binary search range. Our lowest possible target is the minimum single chunk on the board, which is 1. Our highest possible target is the total sum of all chunks divided equally, 45. We also capture the target number of pieces we need to create, which is k plus 1. We run a binary search loop that continues as long as our boundaries haven't converged. In each step, we calculate the exact midpoint. We add 1 before dividing to ensure that our search space rounds upward, avoiding an infinite loop later when checking upper bounds. Now we run our greedy check algorithm. We iterate through our chocolate bar from left to right, maintaining a running tally of the current piece's sweetness, alongside a counter for how many pieces we have successfully cut so far. Let's track our very first check with our midpoint of 23. As we accumulate chunks, we can only form a single valid piece before running out of chocolate. Since one piece is drastically less than our target requirement of 6, this threshold is completely impossible. Because our greedy check failed to hit our target count, our guess was too ambitious. We look at our boundary logic and rule out the upper half of our options entirely. We shift our high pointer down to mid-1, resetting our search space ceiling to 22. The binary search loop repeats this cycle. If a target succeeds, we record it by pushing our low floor up to mid. If it fails, we drop our high ceiling down. The search pointers systematically trap the answer, narrowing the window until they lock onto the exact same number. Once our boundaries collide, the loop terminates. The pointers are both resting on the value 6, which represents the absolute maximum possible sweetness our piece can yield under an optimal division strategy. We return this value to complete our algorithm. N is the number of chocolate chunks, and S is the total sweetness. Time is O of n log S. Each binary search step runs one linear greedy pass, and the answer range from 1 to S halves about log S times. Space is O of 1, only running totals and piece counters, no extra arrays. Our main routine maximizes the minimum piece sweetness after K cuts. Set the search floor to the smallest single chunk. Set the ceiling to the total sweetness of the whole bar. Binary search continues until the boundaries meet. Probe the midpoint, round it upward to avoid stalling. Ask whether we can carve enough pieces at this minimum share. A feasible guess raises the floor to mid. Otherwise the guess was too ambitious. Drop the ceiling just below the failed midpoint. The converged pointer is the maximum achievable minimum sweetness. The helper greedily tests one candidate minimum share. Reset the running tally for the piece under construction. Reset the piece counter. Scan the bar from left to right. Add each chunk to the current piece. Cut one valid piece. And start accumulating the next. Success means at least K plus 1 pieces were formed.